Hello everyone. Now we will hear from Robert about reverse engineering the Nullsoft Scriptable Installed System, or NSIS. Take it away.
Hello everybody. I have to apologize in advance. I have a little bit of a cough, so if I'm just up here just hacking away during this talk, please forgive me. I'm sorry. It has, no, it's actually from, it's not from that. Okay, so the origins of NSIS, so it was developed in the 90s, and so it's from the Nullsoft software company, and they developed NSIS to distribute their own company's software, but what's interesting is it's outlived most of the other Nullsoft products and projects. These are some of the other Nullsoft projects. So Nutella, I think, it's a file sharing, peer-to-peer file sharing, Shoutcast, Winamp. I think you're familiar with that as well. This is today's usage of NSIS. So this is from just this year. These are the count of NSIS detected installers that were submitted. So this is for Reversing Labs, where I work. And this is the total count of detected per month. So there's anywhere from 100,000 to nearly 300,000 new NSIS installers that are at least submitted to our system per month. On the side here, you can see some of the more well-known systems that use NSIS as their installer. So everything that portableapps.com uses is installed by an NSIS installer. Firefox is actually, it has a self-extracting installer, and then inside of that, there are one or more NSIS installers. And then not all, but many games on Steam and other games just in general are installed using NSIS installers. And because it's free, you don't have to pay for a license for the installer, so it reduces your costs for your project. There are a couple of different major variations of NSIS. So there's the official version, there's version 1, 2, and 3. There's another one called NSIS BI, which is big files, so it can handle files over 2 gigabytes. This is the one that was mainly developed because game developers needed to distribute games that had really big files, because you have video and audio and all this sort of stuff that can't fit in the official NSIS. And then I apologize, I can't pronounce the last name, but Marius, he's a developer who makes plugins for NSIS and has also made a fork of NSIS, which is based on version 3. And other than the cool plugins, it also does 64-bit. So the official version of NSIS is only 32-bit. There are a few various builds of the official version, and then also of the other versions. But these are the larger buckets. We're going to get into smaller and smaller buckets as we get more granular as this talk goes on, but these are the big ones. So there's the base model. There's long string. So there's a setting in the NSIS headers before you compile it that sets the string length. So the default string length is 1024, and then long string is 8192 for also, I think mostly for stuff like games and stuff like that, where you need to have like longer single strings. And then there is a logging version. And then if you compile it yourself, you can have all the debug, all the good stuff in the debug version turned on. This is what an NSIS installer script language looks like. So the NSIS installer scripting language, if you think about it, an NSIS installer is basically, it implements a little tiny virtual machine. And we're going to see this in a little bit. I'm going to show you how that virtual machine works. But essentially, what happens is you take the NSIS scripting language, and then you run it through a compiler, which is part of the NSIS scripting system. And then that compiles it down to a little bytecode blob of opcode instructions. And so each one of these, some of these at the top will actually control just flags that get set in the NSIS installer header. And then other ones down, like set out path. Like in this section, you can see set out path and then file, write uninstaller, write registry, binary. All of these are different opcodes, which we will see. And so this is just one example of an opcode. I picked this one out. It's kind of interesting because I don't think anyone actually extracts this one properly. I've noticed nobody, like kind of it's really obscure. It doesn't really get extracted properly by the other extractors. So this is actually so it keeps a registry value that you can write in binary, like you just saw where I said like dead beef, blah, blah, blah. But this actually gets compressed as a file in the overlay. So the content of write reg bin is actually right there as an entry in the list of files. And I haven't seen anything actually extract it properly. So the anatomy of an NSIS installer is the following. You have like two basic pieces. You have an exe head, which is compiled in advance. This is what, so when you build, if you're building NSIS from, oh, that is me. Okay, sorry. You guys move my leg over this way. Do not touch that. Okay, so you have the exe head. And so when you build your entire NSIS installer system, what it does is it pre-compiles each one of the various flavors of the exe head, depending on what you will use. So when someone makes a choice in the installer script, saying, for example, I want compression type bzip2, then what it does is after it compiles your script down to bytecode, it then chooses the proper exe head and just goes dunk like that, and then compresses all the stuff that you need, including your script. All right, so you have the compressed information along with the script, and then all the different files that would need to be installed, and those are in the overlay. So that's in the compressed data part, and then you have the NSIS headers, which are visible. We're going to take a look at what the headers look like. They're actually very small, very simple. And then, as I said, inside the compressed data, you have the NSIS script bytecode. You have an optional uninstaller script bytecode, and then all the files to install, and those registry binary if you have them. So, like I said, we're going to get even more granular. So beyond those flavors that I talked about earlier, you can also have the string type, so ANSI, which is like 1 byte, used to keep one character in the string, and then Unicode, which is a multi-byte string encoding format. And then we can have all of these different types of compression, LZMA2, bzip2, zlib, or no compression. No compression is actually handled by the zlib exe head. There's a execution pathway in there. I won't show you that part because it's kind of boring, but yeah, there's an execution pathway that handles no encryption. And then you have, I mean, I've looked for a word for this, but I don't think Solidity is even really a word. I think it's the name for some company that they, tried to make a corporate company name from it, but I'm going to call it Solidity. So it's like whether the thing is solid or not solid. And so a solid overlay does one single pass of compression, and then a not solid overlay, each one of the files inside of the overlay is compressed individually. So for example, if you have if it's using zlib compression, each one of those files will have its own zlib header. And then if it's a solid, there's one zlib header, and then the entire thing is just one single long compressed string, byte string. And there's a few tools that are out there that allow you to analyze NSIS. There's the 7-zip decompiler. It's still in 7-zip. You just have to change one flag in the headers and then recompile 7-zip, and then it will, it'll reveal the 7-zip decompiler. It's pretty good. And then there's Binary Refinery. Who's heard of Binary Refinery? Yeah, you should go look up Binary Refinery. It's super awesome. You'll find it very, very useful. It includes a decompiler that has a different methodology and different output format than the other ones, and we're going to see the differences. Then there is NRS, which is the NSIS reversing suite, which is mainly focused on IDA and using it with IDA Pro. And then there's Malcat, and Malcat's really awesome. I've used all of these, and this is actually, if you want to, you can take a photo of this. This is the secret code for getting 7-zip's decompiler to work properly. And this is what 7-zip's decompiler output looks like. So if you remember the original NSIS script, what their goal was to make something that looks very similar to the original NSIS script. So their goal is to give you something that matches the original NSIS script as closely as possible. And so this is what the configuration section of it would look like. And then this is where the instructions and function labels and stuff like that, section labels, etc. You can tell this has all these sort of gibberish words here. This is malware. This is a malicious NSIS installer script. And then this is what Binary Refinery's output looks like. So you can see there's a count of position on the left side. So that's basically each NSIS instruction or opcode is of a fixed length, or fixed width, if you will. And so each one, you can actually line them up. And so this is the count or the offset from the very first in the NSIS bytecode block. And we're going to see that in detail in just a minute. And then this is what Malcat looks like. So yeah, Malcat actually does a really good job of differentiating between jump and NOP, because the jump opcode and the NOP opcode are actually overloaded. So the opcode is the same number, but the content in the immediates is different. So the way you differentiate a NOP and a jump is by looking at the content in the immediates, the immediate values. So they're actually the same opcode, and you'll notice like some of the decompilers out there don't differentiate between the two, so it makes it a little difficult. And so I needed to write a new tool set. So there's a few reasons why I decided to write a new tool set from scratch. The first one, the LZMA2 and the zlib decompression in NSIS can be handled just fine using all standard libraries. You can use whatever implementation in whatever programming language you'd like to do, it will work just fine. bzip2 will not. And I'll cover exactly why in a minute, but yeah, bzip2, you cannot use any of the standard libraries to decompress it. You can't use the bzip2 implementation that NSIS does, but bzip2 in general, you can use any implementation, but you can't with this particular one. Malcat does the best of all of them right now, hands down, one of the best implementations. But it's also proprietary software. There's a free version and all that, but it's still proprietary software. Malcat is also very super awesome, not expensive. I recommend buying it and get the real one. It's actually a very good piece of software. 7-zip has the problems that I just mentioned. The people that run 7-zip have decided long ago that maintaining the decompiler for NSIS is outside of the scope of their project. So they have deprecated it, and then it's no longer being maintained. So it's still in there because it doesn't take up space just to have it in the source code. But yeah, it's disabled by default. And so I tried to pull all the bits of the 7-zip decompression and stuff like that out that I would need to, but unfortunately, that's not an easy lift for me. It's been a long time since I've done the C++ forward engineering, and so all of the code pathways and what you need to do, it's all very deeply intertwined with all of the 7-zip code. It's not just in the files that cover NSIS. So NRS, this one is also pretty good, but they clearly ran into the exact same problem I did and the exact same problem everyone else did, where bzip2 is somehow different and it doesn't work properly. So their solution was to take the precise C code from NSIS itself and then wrap a swig wrapper around it so that it could be implemented directly in Python. However, I tried to get that working and it doesn't work. And I know that I'm not the only one that couldn't get it to work, because it also doesn't work in assembly line. So, other people who are very good at what they do, also it's not working for them. So there is something in there. I tried to take the latest version of Swig and figure out how to get it all working, but again, it got very annoying. I couldn't get it to work the first time, so I was trying some other stuff. And I found Binary Refinery. Binary Refinery, again, ran into the same problem. So they resurrected some ancient abandoned Python project called PyFlate. But PyFlate has a really interesting warning in there. It has a really interesting warning in there. I didn't actually give you a screenshot of it, but basically it said something along the lines of, PyFlate basically says something along the lines of, I don't know what's going on here, so that made me uncomfortable using that particular piece of software for mass processing, because if it doesn't decompress the data properly, there might be something, some little wiggle in there somewhere, and I might miss a particular piece of malware without having something that's very precise. So, why does the standard bzip2 implementation not work? I actually don't need video, I can describe it to you. So, it's super easy. The bzip2 that they use, they made the decision, and this is smart. bzip2 has very specific headers, and it also has so it has really specific headers that they removed. And then it also has end headers that they also removed. So there's some data at the beginning and the end of the bzip2 compressed blob, and they removed the stuff at the beginning and the end, and they removed it because they control the compressor and they control the decompressor. So they don't need any of the stuff that they would have needed had they been writing a decompressor that you're being given random compressed data from lots of different sources, different compressors, different implementations, and blah, blah, blah. Then you might need some of these headers and tail headers or end headers. But for this, because they are the NSIS is the thing that actually compressed it and then decompressed it, these things are not needed. But what that means is you have a completely different implementation where it's missing the headers at the beginning. That you can fake, by the way. It's pretty easy to just figure out what you need to do to put a fake header on there. But then finding where the end is supposed to be without having the headers there in the first place was very challenging. So that's something that I was trying to do, to figure out if I could fake it and throw some data that looks right at the end and try to find the end. That proved challenging as well. So what I did was I took the bzip2 NSIS original source code in C, and I rewrote it from scratch in Python. So basically, literally line by line, instruction by instruction, block by block. And this is where you start. So this is the main decompression function. So this is BZ2 BZ decompress. It calls a run length encoding or an unrun length encoding function, which comes in two flavors, fast or small, and only one of them you need to do. I somehow chose the more difficult one to translate to Python, but it's fine. And then it calls decompress. Now, one of the things I learned is that this is some ancient technology from like the 90s, right? So computers back then didn't have the ability to load as much data into memory as you would need to decompress something all at once. And so it had all of these crazy state maintaining functions, or not functions, but state maintaining variables, where it would actually it would save the state, and then, is it still having a problem?
No.
Okay. So it would save the state, and then it would go back to the parent function, and it would ask the parent function for another block of data, and then it would decompress that block of data until it hits a particular, a good stopping point, let's say, and then it saves all its state out, and it keeps doing this over and over. So one of the things I had to do is basically remove all of that, but it had all of these different, these really wild, very detailed state staving features. And then there's the other thing that really was fun. So if you're C, this is C, so if you're a C programmer, you're familiar with macros? Yes? Macros? Okay, so they put the case for a switch statement inside of a macro. Yes. Okay. So I had to basically kind of, smooth everything out and unwind. And they weren't just one macro. If you'll look, you'll love this. So that the case is actually in a nested macro. So you have get uchar and get bit, and then inside of those they call get bits, and then inside of get bits it has case, and then LLL, which actually contains the number of the case. So, welcome to the 90s, I guess. So I had to really, and there's more. This one was fun. This actually has some of the get bits inside of another macro called get move to front value. And so one of the first challenges I had was basically just unwinding and inlining all of the macros. So just, and so then after I unwound and inlined the macros, I get this, flat C code. And so then what I did was I wanted to have a unit test, sort of a unit test. So what I did was I used x64dbg and a NSIS installer, and I basically just ran it until it decompressed the installer script itself. So I used the ground truth of the actual uninstaller itselth, and I took the installer script code, the bytecode blob of the installer script, and I calculated SHA-256 of that, and then I used that SHA-256. I compared the result of what I was doing in my code translation with this after every code change. And so, I'm also not a very good C programmer, so I literally was using command line stuff in my C. He's laughing, but it doesn't matter because I'm leaving. I'm leaving C. I'm like getting the code out and like going into the escape spaceship with my Python, So, it doesn't matter that this is ugly. It worked. And then I needed to have something printed. So I needed to have something printed on every single line. After every single instruction, I needed to have something printed. So I asked Hetty to print it, and he said, print it for yourself. So I wrote all of these print functions. So I've got and I don't know, these are some that I wrote myself. I don't know if I wrote this very well, but I know that it actually put out the information that I needed.
Could have used a macro.
Oh, God. And I'm sure, yeah. Macros give me hives now. Okay, and so then I made these even bigger print statements where I print the state. And then I realized halfway through making these giant print statements for the state is that I don't need the state. I could just do all of it at once and then ignore state completely. Just jam all the compressed data into the function at once, like all of it. And then it doesn't care because it never has to keep state because there's no reason to keep state because we have modern computers which can load the entire compressed data into memory at once. But that's okay. And then I wrote this cool little mini hex dumper that I tried to make it look like the command line hex dump. And then there's what I called the noodle extruder. So if you're familiar, is anyone familiar with how bzip2 actually encodes the data? Like, what does the bzip2 data look like? Does anybody know? So it's not a series of bytes. It's actually a series of bits. So it's a long bit stream. And so what happens is if you, for example, if that bit stream is shifted for any reason to the left a little bit, or if it's, if it changes a little bit over here, all the bytes look different because it's not a stream of bytes, it's a stream of bits. And so each bit is on a line. So it's like having a noodle. And so there's a function called getBits in there, which you tell it how many bits you want to get from the bit stream, and then it gives you that set of bits in a row, a little row. And so this is the noodle extruder. I kept it because it's useful, it makes sense. This is one of the things that did make sense, not the macros, but this made sense. There's a few things that I noticed along the way. It's like when you're reverse engineering something, you kind of notice things that the author who doesn't look at the resulting machine code, they don't see that. So if you're writing something in source code, unless you're actually looking at the assembly and the machine instructions that are produced by your code, you may not actually notice this sort of stuff. And I know that this is something that they missed because this is a compressor. And so using less space is better with a compressor. So I have no other real reason to understand why they would do this. But so the selector 1 at the top stores a number in 3 bits, right? So it's a 3-bit number. And then BZ selector 2 stores a number in 15 bits, okay? Then you've got selector 3, which the number that it can store is actually smaller than a number that you can store in 3 bits, but they decided to store it in a null terminated bit stream. So for like 2, it would be 1, 1, 0, and then for like 5, it would be 1, 1, 1, 1, 1, 0. Did I say the right number of ones? Whatever. But you know what I'm saying. So what they could have done is save just a small amount of space because they end up storing data in a much more in a format that takes more bits than they could had they just stored it in the same way they had stored selector 1, and they already had a function or a set of instructions that takes that 3-bit number and then turns it into a number that they can use elsewhere in the code. So I couldn't figure out like what they were thinking there, but who knows? It's something that you see when you see how things are stored. And then I also noticed some maybe they're just paranoid and they were hoping, or they thought maybe the pointer might get corrupted at some point during execution, but they check whether the pointer is negative in places where they've already checked whether the pointer is negative, like a couple of functions earlier. So maybe it's just paranoia, but these are some of the things that you notice along the way. And this is that same function. This is where they checked it earlier. And so the result is just a single flat clean C file. I kept it around. This is not actually part of the project anymore, but I just kept it around just for my mental notes and to see how it was done, just so I can, go back to it and look at it. So then I went through and did a line-by-line rewrite in Python, and this is actually a hint. If you do Python, this is a fake unit test, and what it lets you do is write unit tests in a format where you can just copy and paste it into your real unit test. It already looks correct. It's already in the correct format, but that self is actually just a variable, not a real self-referential case method. All right, and like that. So it makes it easy to write the unit test. You see that one down at the bottom? You'll see this again right there in the exact same format. So it's just you can cut and paste, because you should always be writing unit tests. This thing has 100% unit test coverage. And I kept the SHA-256 test, which I went through the whole Python translation as well, and maintained the correctness based on this SHA-256. Now, I refactored goto, so that was one of the challenges beyond macros, is what to do about goto. And so my initial choice was to translate gotos into recursion. And what I learned is that there's actually a limit of recursion depth in Python. And so the maximum recursion depth in Python is 3,000. And so to do some of the really large installers, the ones that are solid bzip2, where the entire overlay is like one big bzip2 compressed piece, you have to set it to 1 million recursion depth. And then it also gets a little bit slow. So there were some issues there. And so what I talked to someone who's much smarter than me, and he helped me figure out like what the changes should be. And so I changed this over to putting some returns and continues and breaks and stuff like that in smart locations. And I was able to clean it up, make it fast. And then at the end, I realized, again, a lot of the code pathways that are in those weird locations, therefore they're there to save the state off in between compression runs. So I didn't even need to do most of this anyway. A lot of it doesn't even execute if you don't have your state being saved. So the result of this is NSIS unbz2. So it's open source. You can install it from PyPy. It is pretty solid. I've run it through hundreds and hundreds of thousands of NSIS installers. And so then the next step is to make a reverse engineering framework. So the NRS was the one that goes with IDA, but I don't use IDA. I use Binary Ninja, so I needed one that works with Binary Ninja. And so I've begun the process of creating a full feature reverse engineering framework. And so the first thing you notice is you need to know, you need to understand the difference between the different exe heads. And so that up there is, these are the functions that are different in the zlib. So those are all the zlib decompression handler functions. This middle one, that's the LZMA handler functions. And then this monstrosity down here is the bzip2 handler functions in the bzip2 exe head. So those are really the only functional difference between any of the exe heads. And so then what I did was I boiled the ocean because I wanted all the NSIS installers. So I found all the NSIS installers. I wrote a bunch of web scraping scripts to go and get my IP banned from SourceForge, and then I changed my IP and then get that one banned. And then eventually I got all of the different NSIS installers. I got the NSIS BIs, I got all of the regular NSIS, I got all of Marius's NSIS forks and everything. And I got all the different flavors. So there's like some that are zip files, some of them are themselves NSIS installers. And so what my thought here was, if I know all of the NSIS installers, I've got all of them in front of me, I've got all the XE heads, and I know exactly what they all are, what I can then do is those functions that we saw earlier are the difference between the NSIS flavors. There's also the solid and not solid, and then there's also the Unicode and ANSI string. And so you have 12, right? I think 4, 8, yeah, so you have 12 different variations. And so what I did was I calculated what the hash of the text code section is. So that's where all the differentiation is. And I made this thing called stub ID. And I realized after I called it stub ID, it sounds like stupid, which it is. I mean, it's really stupid, but it works really well. So what I have here is basically a calculation that takes the text section. It actually looks for all the sections, and the reason why it looks for all the sections is for different packers like UPX and stuff like that. And then this I actually hard-coded. So what I did was I calculated the size of the text section in all of them, and then hard-coded the text section size. And the reason for this is with UPX, you have UPX starts with a big empty section where it will write the code, the executable code, but it's empty and it's actually compressed in a different section. So this works only after you've run the UPX unpacking code, and then you can get the section size of the NSIS code. So stub ID, and this is how I'm using it, and I use the stub ID result, which is like a set of YAR rules. I think it's like 40,000 or more YAR rules, and then it lets me know whether it's zlib, LZMA, bzip2, solid or not. And so going back to our NSIS installer anatomy, we're going to look at some of the script bytecode itself and what that sort of stuff does. And so, and by the way, sorry, I skipped ahead a little bit. Sorry, we're going to talk about NSIS installer headers, and these are they're actually part of the overlay, but they're not compressed. And it looks like this. So the first byte all the way over there is the file header flags. So that's FH flag. And then the next set of bytes are, these are the magic number. So they have, dead beef spelled in little endian, and then Nullsoft INST. And then the next two fields, one is the size of the script. So that's the size of the decompressed NSIS installer script. And then the next one is the size of the archive. So that's either the compressed size of the NSIS and script, or it's the compressed size of the entire, for solid, it's the size of the entire solid overlay. And then 5D indicates that this one is LZMA, and then 80 indicates that it's a compressed overlay. And then these are some of the flags that can be stored in FH flags. So you have force CRC, no CRC, silent, and uninstall. So uninstall shows that this is an uninstaller script. So in my Python code, I liked the idea of the bitstream reader, and so I made a little soft serve ice cream machine. I know that you can just do reads. I understand that you can just do reads off of data, and that's what I'm doing here. But I also wanted to have something that shows like what it was that I was trying to read, so I can give it a good error code if something goes wrong. And so then this is the bzip2 decompression handler inside of the reverse engineering framework that I wrote. And I invite you, please go look. It's on GitHub. Again, this is on PyPy as well. You can just, pip install it. And so then what I saw was I need to get something that can mass process NSIS installers. And I saw that, the assembly line has a service in assembly line called extract. And it's using its own fork of NRS. And so even this fork of NRS doesn't do the bzip2 correctly. So I had a bunch of problems installing assembly line. The documentation had been not used by many people recently. So I made my own installer script. So this is just to get Docker up and running. And then this is the Docker variation of assembly line. This is the Docker appliance deployment of assembly line. And then I went through and made sure that the microcates appliance documentation was also correct. And then I submitted a bazillion pull requests for the documentation. So I fixed up all of the assembly line documentation. Now I feel like I'm the volunteered maintainer of the documentation, so I got to go back and make sure it stays correct. I'm not actually the maintainer. They're just very nice guys, but they actually accepted all my pull requests, which is one of the nice things. And so then this is the change that I made to the extract service, and I have both my decompressor and reverse engineering framework used, and I'm also using binary refinery so that you can get both. It provides already the one that looks like 7-zip from the NRS framework, and then you get the decompiler from binary refinery, and then you have the accurately, byte for byte accurate decompressed bytecode script from my code. And this is the function that does all of that. And so now you got before one decompiled NSIS installer script, and you wouldn't get it always, because if it's bzip2 it would be missing. And so now you get 3. You get the non-decompiled, the bytecode version, and then two flavors of decompressed or decompiled version. Now, this is an Easter egg, or kind of just a bait where you want to come talk to me. I have a way to detect NSIS installers under all circumstances, and it's not code-based, and none of the adversaries know about this. I nail all of them, even the more advanced GULoader stuff and all of the Chinese APTs that abuse NSIS. None of them know this, so I have a way to find all of them. Come find me, and we'll do like a TLP Red talk over there in the bar about how to actually detect all of these. So let's do some malware analysis. I'm going to try to move this real quick. So we have the different types of malware. There's a simple dropper, and this is where it installs the malware like it's a regular installer. There's no thought. They're not doing anything clever. Then there's a custom build, so it's just not one of the official NSIS distributions. They've just built it themselves and either changed something or built it themselves and used it. And then there's an obfuscated custom build where they're actually doing code changes of some kind to hide that it's NSIS. And then the next level of complexity is someone who is using the scripting language itself to do something malicious, like download, writing the downloader code in NSIS installer script language. And then you have the shellcode loader. So this is like the most advanced type. This is GULoader, and we'll see that. So this is an obfuscated custom build. On top, you can see one of my test files. And then down here, you can see this is, I believe this is a Chinese APT or Chinese related. I think you shared this one. This is the one that you pointed out to me a long time ago. But yeah, it's China theme. I mean, it might be, who knows who it is, but this just shows how you can take the magic number and then just basically stomp on it and then change it with just other random bytes, and it would still work as its own NSIS installer. You just couldn't take that exe head and switch it with any other NSIS installers. And this is what they did. They literally just changed those constants in the source code. And then this is another variation. This is where they actually mess around with the source code and rebuild it. Now, I'm not quite sure whether this isn't just the compiler making a choice over the adversary actually changing something, but you would have to see this. You're going to look very carefully to even see it, but it's basically using decrement EAX on that side, which is that's the official NSIS installer. And then this one, this malicious NSIS installer, it's using subtract 1 from EAX, which does exactly the same thing. So that's one of those things where it could go either way. It might be the adversary doing something. It also just might be the compiler that they chose to use did a different type of calculation for this. So it could go either way. This is a downloader, which is abusing the NSIS script. So you can see up at the top, it's loading inetc DLL. And then in yellow, you can see the two URLs that it's trying to download the next stage from. And then down at the bottom, you can see where it has written the downloaded next stage to an executable file, and then it's running it. Now let's take a look at GULoader. So this is my favorite. This is my long-term enemy. So this is an example of one of the ways that they abuse NSIS installer scripts. And basically, they're juggling data from different files. So there's all sorts of files that look like junk, and then they read a few bytes or read some data from all the different junk-looking files, and then juggle it around through code pathways in NSIS installer language, and then finally put it all together and run systemdll to call a function, like for example, virtual alloc, or many different malware API calls. Here again, you can see another example of it. So they push the var124, which contains that instruction, and then they call it with register DLL and from systemdll. This is that same instruction. You get to see it in Malcat. So this is the Malcat view of it. Now I want to show you some important NSIS installer functions in Binary Ninja. So these are the major functions that you would need to know. So this is get NSIS string. Let me try to make it a little bigger. Can you see that? Yeah, it looks pretty good. Okay. So this is get NSIS string. So what this does is it actually, for any of the instructions that need to use a string, this will actually take the address of the string and then return the string. So you need to see this one if you want to reverse engineer NSIS very well. Another one that is important is this one. This is the main virtual machine that implements basically everything in NSIS, and it is called execute entry. Yeah, here we go. So this is just where, this is kind of the preamble, and then it hits this jump table. And the jump table implements all of the different opcodes. And I submitted a bug report to Binary Ninja literally like 2 weeks ago to get these opcodes looking like English so you can read them. So that's awesome. Thank you guys. It made this presentation look good. But yeah, so now you can see all the different opcodes. There are 0x43 different opcodes, and then there are operators, so add, subtract, multiply, divide. So this literally implements an entire language in a VM. And so each one of these, we can actually switch to the IL in linear mode, and there we go. And you can see what it'll do is it hits that switch statement, the one with all the macros, and basically distributes where, like whatever opcode it is, it'll go to the correct case and then execute the code for that particular opcode, be it sleep or create directory, all of these sorts of things. And so what you want to do, let me go back to the slideshow. So this is a really good video that no longer exists, and I really am sorry. I want you to watch her. She's a very amazing reverse engineer, and she had a 7 hour video of her manually reverse engineering a GULoader sample. It is a fantastic video. Unfortunately, there was some dispute with YouTube on having security videos, and so I don't want to actually speak for anyone. Just watch her video and her complaints. Basically YouTube is being no good. But unfortunately, the video I wanted to show everybody is gone, and one of the other options, so she basically went through and literally went with the documentation and looked at the documentation for each command and then figured out what it does and then figured out where the data comes from and basically by hand reverse engineered an entire sample. One of the other things you can do is you can do a brain transplant, which is what I call it. So you can take, because the exe head works with, and the script will work with any of the same version of exe head. So you can take the exe head from the malware, remove it, and then put on the same version that has the logging turned on. And so you can have the logging exe head stuck onto the overlay from your malware, and then it will log the instructions that it can. But it doesn't have the greatest logging, and so this is the next step that I've done, which is find each one of those locations in the VM function, the execute entry, and then also the function that calls it, and then just put in x64dbg logging via breakpoints. And so that leads you to this, and this is actually my last bit, but we will see if this actually is visible. Yeah, and so then you end up with this, and might not be big enough, but let's see. Oops, I want to click there. Yeah, so this is not very big. I don't know how to make this bigger, but I'll just kind of describe it to you. This is my last part of the presentation, but basically with those logging statements in x64dbg, you can do a number of different things. So you can see what position, so over there it'll say POS 23, and that position lines up with position 23. So you can see in Binary Refinery's decompiled version, you can see 23 is here. Yeah, so you can have it log the position, which is what position it is in the script, and then you can have it log the opcode. So 23, 26, 21. That's these. So you can see where it's going in here. And then you also, this will reveal that, for example, down here where it starts at position 49, so that would be down here. Oop, went a little bit too far. Sorry, this is too small. Yeah, so here you can see it position 45. And then we can look over in Binary Refinery, and then position 45, this is kind of funny, they're abusing is window as a conditional. So this is not, you're supposed to give it like an actual window, not gobbledygook, but they're using it as a condition, as like a fake conditional. And then, this is a little trick, because it'll have a fake conditional and then quit, but quit is never going to run. But then it has a sign variable, and you can see here this is a massive loop, so 103,232 iterations. So this is just to really make a reverse engineer angry, because all it does is count all the way down and then move on to the next thing. But you can see this NOP here, 4C, this is actually not a NOP, that is actually a jump. So that's the jump that goes back. And this you can see a little bit better in Malcat here. So you can see is window, jumps, you never hit quit, you assign, and then you can see this is actually a jump, not a NOP. And that's what I was talking about earlier, where some of these decompilers don't actually look at the immediate to figure out whether something is a jump or a NOP. So, and then my last slide is that I have planned for the next stage of this whole project is two things. So first of all, I'm working on a Binary Ninja architecture plugin so that you can just take an NSIS script and open it in Binary Ninja and then see all of the different opcodes and see all the loops and everything like that. And then when I'm done with that, like I want to use that to write a pure Python NSIS emulator so that you don't need to use any of this other stuff. You can just decompress the script, run it in the emulator, see exactly what it does. So I don't think we have time for questions, but thank you, everybody.